Again, to explain some new things. As you know, we have finished section 1 in chapter 1, and for today we'll start by some of the most important concept to know, which is colligative properties. What are the colligative properties and why we call them colligative, and what is the reason why we study this concept individually? Okay, so these are some questions. By the end of this video, you will know the suitable answer for each of those questions that I said. Well, I want to say something before starting anything. What we have to do through this section, I mean section 2 in chapter 1. In anywhere, we're going to compare between a pure solvent and same solvent, but after something dissolved in it to producing a solution. So, comparing between pure solvent and solution is our main goal in terms of colligative properties. Let's see. Firstly, we have, as always, we have a definition, so I don't want to mention the definition directly because we don't know nothing about the definition if we don't have any idea. Well, what are the colligative properties? Suppose that we have a glass, okay, filled until here with water. It's pure water. Pure water. And we know that pure water freezes at 0 Celsius degree, boils at 100 Celsius degree. But what will happen after dissolving some sugar? If we dissolve some sugar in water, what will happen? Of course, it behaves differently. It behaves different from its original case, which was pure solvent, pure water. What's gonna change after something being dissolved in pure water? Here we have 4 points that are changed with adding a solute into any solvent. Let's see. Okay. Colligative properties are properties that depend on the concentration of solute particles, irrespectively to their nature, to their identity, rather than their identity. It means we have some properties that are dependent on the concentration, the number of particles, not their identity, not their behavior, not the type of compound. Only the concentration, the number of particles are important for colligative properties. Here we have 4 colligative properties. I want to mention again, look, colligative properties are properties that depend on the concentration or number of particles is the same. Number of particles. When we say number of particles, it means concentration of solute particle. Number of solute particles, but not their identity, rather than their identity, irrespectively to their identity. Okay. We have 4 properties which are vapor pressure, just for now, just vapor pressure, freezing point, boiling point, and osmotic pressure. What will happen if we have a glass of water, H2O, and then we dissolve some sugar? What will happen to those properties? Firstly, vapor pressure decrease. It means if we have pure water and then we dissolve some sugar into water, vapor pressure gets down, decrease, okay, depresses. It decreases by adding some solute. Freezing point depression, it means freezing point will decrease, same as the first point. Well, freezing point depression, it means delta TF, and it's always negative. Remember, It's always negative. It must be negative. Always, always. Third point, boiling point. What will happen to boiling point? It increase, it raise, it elevate. So boiling point increase with adding a solute. Osmotic pressure, of course, it will raise, it will increase. So two of them are decreased and other two are increasing by adding a few amount of solute into a pure solvent. Well, now I want to classify, I want to classify a solute property based on their tendency of vaporization. Well, we have two types of solute, one of them called non-volatile, another one called volatile. Well, non-volatile, it means we have something that don't want to vaporize easily, doesn't likely to vaporize easily, okay? Non-volatile, something that don't want to vaporize easily, okay? In contrast, we have volatile, it means something that vaporizes easily. For example, benzene. Benzene, the commercial gasoline, we know that it will vaporize easily. So it's called volatile. But oil, it won't vaporize easily. So called non-volatile. Benzene vaporize easily, it's volatile. But oil doesn't vaporize easily, so it's non-volatile. So we're going to deal with volatile one. Non-volatile solute lowers freezing point. I just explain it. What will happen to freezing point? Lowers freezing point. And vapor pressure also decreases, lowers vapor pressure. But boiling point and osmotic pressure, they increase, they raise by adding non-volatile solute. As much as the concentration increase, there will be, look at here. I'll mention some important thing. So please write down all of these things carefully. Let's see. Vapor pressure lowering. Vapor pressure lowering. As much as the concentration increase, all of the following phrases increase. They increase with increasing the concentration of solute. They are dependent on the concentration of solute. It means if we increase more solute, so there will be more lowering. But mister, I almost confused what's the difference between vapor pressure and vapor pressure lowering. Look, by adding solute, vapor pressure decrease. As much as the concentration increase, there will be more lowering. That means vapor pressure decreases more. So just vapor pressure as reverse with concentration. But lowering of vapor pressure, it's directly changed with changing the concentration. Freezing point, look, if we add more solute, there will be more depression. So only freezing point is reversed with concentration. But depression of freezing point is directly changed with changing the concentration. So if we increase concentration, there will be more depression. Same for the boiling point and osmotic pressure. Well, from now on you have to know that. In anywhere, if you see this question, why vapor pressure is a colligative property? Why freezing point is a colligative property? Why boiling point, why osmotic pressure is a colligative property? Generally, I can say why X is a colligative property. Why? Why X? X is anything. Could be vapor pressure, freezing point, boiling point, or osmotic pressure. Why they are colligative property? Immediately you have to say, because they depend on the concentration of solute. Why Z is not a colligative property? Because of they don't depend. Why X is a colligative property? Anything called colligative property, it means it depends on the concentration of the solute, surely. Well, so here it's a wonderful picture I found in internet. Colligative property we have for osmotic pressure, elevation of boiling point, depression of freezing point, lowering of the vapor pressure. And for the first one, now I want to mention of lowering of vapor pressure. Well, let's see how vapor pressure changes by adding some amount of solute into a pure solvent. Good. Before reading anything, I prefer to open a new page, okay? Because if I draw something, it's better for you and you can understand very easily by comparing to reading the phrases in my pamphlet. Okay. As I told you, you have to compare pure solvent into a solution. I mean, the same solvent, but after something being dissolved in it. Suppose that we have a... okay, very good. This is a glass, okay? The first case, it's filled with H2O. Okay, very good. Well, we have a glass filled with H2O, okay, until this level. So any of these particles is H2O molecule. So here, the first case, A, pure solvent. Pure solvent. Here is pure solvent. So if we heat pure solvent, what will happen? We know that the temperature begins to rise, right? After heating, the temperature starts to rise. So, in this case, the water molecules receive more energy, okay? So each of them can vaporize easily because, look, the first case is a pure solvent. When we heat a pure solvent, for example, water, okay? If we heat pure water, there's only a molecule of water. Only a molecule of water. So what will happen when we heat a pure water? There's only a molecules of water, so there's no barrier in front of them. They will receive, when they receive enough energy, immediately they can vaporize easily. So they can escape inside of the liquid into a gas phase so easily. Why? Because there's only a water molecule and a huge number, by a huge number. So there's no barrier in front of them. When they receive enough energy, immediately they will vaporize. They will escape. They will escape inside of a liquid into a gas phase. So I expect here to get, they yield more vapor. So vapor pressure is high. First case, because we have only a molecules of water inside of the jar, inside of the beaker, inside of the bath, glass, whatever, there's no barrier except of water molecules. So when they achieve enough energy, they will vaporize easily, just like this. But now, let's repeat the same case. Remember, I told you we're going to compare by a solution. So we have the same glass of water here, same glass of water, okay? But this time, it doesn't contain only water molecules. Here, It's H2O. H2O molecules. But this time, we will dissolve a solute. For example, sugar. I just dissolve it. Some sugar here. Some sugar molecules. Now, if I ask some question, which one contains more water molecules? Oh, mister, it's so easy, this one. So, which one produce more vapor? Because of here contains more water molecules, so they produce more vapor. Why? Because here some water molecules are replaced by sugar, which is C6H12O6, for example. C6H12O6. Because some water particles are replaced by sugar, okay? So what will happen? As much as sugar molecules increase, there will be fewer number of water molecules. So there will be less water molecules to be vaporized. And now what's your expectation? In which case we will get more vapor here. Why? Because of it contains more water and there's no barrier. But here, when this water molecule starts to vaporize, because of this barrier, it will return back. So there will be a fewer vapor molecule. So fewer, it means less vapor and less vapor pressure. And now we can say here we have a solution, but here is a pure solvent. Case A, case B. So vapor pressure of pure solvent is higher than the vapor pressure of solution. Why? Because of as much as solute particle increase, the relative number of solvent particles decrease. So there will be a fewer number of solvent molecules to escape, to vaporize into a gas phase. This is why as much as the concentration of sugar increase, water molecules decrease, so vapor pressure will lower. That's why we have to say, okay, that's why we have to say lowering vapor pressure decrease. Hopefully you understand deeply about vapor pressure. There's nothing at all. It's super easy and I can say peasy. Well, vapor pressure is the pressure caused, firstly, vapor pressure. If we focus on water vapor pressure, we can see that it contains vapor, which is gas, pressure. So it's a pressure for a gas molecules. Super easy. It's the pressure caused by molecules in a gas phase that are equilibrium with a liquid. It's just a simple definition. You have studied this definition in grades 11 and 10 and surely, okay, and in many other years you have studied this definition. For this year, just read it and it's nothing. So vapor pressure is the pressure caused by molecules in a gas phase which are in the equilibrium with the liquid phase. And now we have some questions. Let's read them. Vapor pressure of solvent containing non-volatile solute, of course, is lower than the vapor pressure of the same solvent, but in a pure case. Or why vapor pressure of a solvent decrease by adding a solute? Why decrease? Because as much as the number of solute particle increase, the number of solvent decrease, so vapor pressure will decrease. That was vapor pressure. Why vapor pressure is a colligative property, remember? Because it depends on the concentration. I showed you. Well, so when now I can tell you now, if I ask you the lowest vapor pressure, it means maximum cons. As I told you, as much as the concentration increase, vapor pressure gets more decreased. Okay, there will be more lowering in vapor pressure. So if I say the least vapor pressure, the lowest vapor pressure, the minimum vapor pressure, these expressions answered by maximum cons, least, lowest, minimum vapor pressure, it means maximum cons. Look, which of the following solution has the lowest vapor pressure? Lowest vapor pressure, it means maximum concentration. So which one contains maximum concentration? First of all of them are glucose. Look here, 0.2, 0.02. So between A and C, A is correct. But now because of answer of B is bigger than both of them, so we have to select B. B is the right answer. So it has minimum vapor pressure, minimum freezing point, maximum boiling point, and of course osmotic pressure max. So each of the following expressions, minimum vapor pressure, minimum freezing point, maximum boiling point, maximum osmotic pressure, they answer by maximum concentration. So we just finished the vapor pressure. And now the second one, the second colligative property, freezing point depression. Freezing point depression. What is freezing point depression? Again, water freezes at 0 Celsius degree. Look, here is freezing point of water. What a wonderful handwriting I have. Look here, 0 Celsius for water, H2O. Water freezes here, 0 Celsius degree. If we add solute, what will happen? Freezing point decrease. So there will be a negative value. Water freezes here. For example, -1, -2, -3 Celsius degree. So water, by receiving some solute, it will freeze below 0 Celsius degree. Why, mister? Because freezing point is decrease. Okay? It's reversed with a concentration. And now freezing point depression, they just convert the equation of solving question into a handwriting as a definition. Freezing point depression, delta TF, is the difference between the freezing point of pure solvent and solution that contain non-volatile solute. So you have to memorize this one. About the molar freezing point. Molar freezing point, it means Kf. Molar freezing point constant, Kf, is the freezing point depression of the solvent in 1 molar solution of non-volatile, non-electrolyte solute. So these are two definitions, just memorize them. I don't want to talk about any point from those definitions rather than their equation, their property, their units. Let's see. We have two equations for the freezing point. Firstly, delta TF. Look, you just need the following equation. The following equations. Let's see. Delta TF equals to freezing point of a solution. Freezing point of solution in Celsius degree. Firstly, it's in Celsius. It's in Celsius. Is in Celsius degree. So these are units of each of the following. Each of the following member of this equation. Delta TF, which is freezing point depression, equals to freezing point of a solution in Celsius degree minus freezing point of a solvent. If solvent is water, we know that solvent freezes at 0. For water, this is equal to 0 Celsius degree. If not, it will be given. Again, if it's not unknown. Well, So freezing point of pure solvent, if it's water, it's 0. In other case, it will be given or it will be calculated. It will be calculated if it's unknown. This is first equation. Delta TF equals to freezing point of solution minus freezing point of pure solvent. Freezing point of pure solvent, it's 0 if solvent is water, and if not, it must be given. About the second equation, delta TF equals to KF times molality. Delta TF, same, they are same, it's in Celsius degree, okay? Delta TF equals to KF times molality. KF is molar freezing point. Again, if it's water, you have to know molar freezing point is negative 1.86. 1.86. Don't forget this number, it's very useful. So if the solvent is water, freezing point of solvent is 0 and KF it's negative 86. But if the solvent if solvent is not water, so it must be given. It must be given also if they are not unknown. That's the equations for solving any mathematical equations, any mathematical questions about freezing point. Okay. Let's see something more. Now we have two equations. I'm going to mention here again. Delta TF equals to freezing point of solvent minus freezing point of solution, sorry. Delta TF equals to freezing point of solution minus freezing point of pure solvent. So pure solvent. Delta TF equals to freezing point of solution minus freezing point of solvent. Another one, we have delta TF, which is equal to KF times molality. Look, the first section of colligative properties problems, I mean mathematical problems, we're going to solve those questions that contain non-volatile, non-electrolyte. But the second part comes with electrolyte. So please, I know that there will be something more, but because of we have to mention non-electrolyte firstly, that's why I forget about the rest. But next part, we will deal with the rest part of this equation also. Well, please memorize the following equations. They are so important. Freezing point of pure solvent equals to 0 if it's water. KF equals to negative 1.86 if it's water. But if not, they must be given. About the molality, hopefully you remember what's molality. I told you, I explained it in the first lecture. I remember I have talked about molality and molarity. Molarity equals to mole of solute per kilogram of solvent. So here we have one step before doing anything through any question. First step, solute and solvent must be identified, and any information about of solute must be turned into mole, if not. And kilogram related to solvent, kilogram. So solvent, if you have any information about the solvent, it must be in kilogram. If not, you have to know the conversion factor between gram and kilogram. Let's solve some mathematical questions about freezing point. Okay, what is the freezing point depression? Freezing point depression, we know it's delta TF and must be in negative sign, negative arithmetic sign. What is the freezing point depression of water in a solution What is the freezing point depression of water in a solution of 17.1 grams of sucrose that dissolved in 200 grams of water? It means we have 200 grams of water, and then we dissolve it 17.1 grams of sucrose, C12H22O11. What will happen to freezing point? You remember, pure water freezes at 0. But after dissolving sucrose, of course, it will get lower. So the result must be in negative. That's why I say it must be in negative, because normally, naturally, water freezes at 0. But now we added something, so it freezes below this normal number, which is 0. It means negative value. Well, first step, you have to identify solvent and solute. Look, dissolving sugar in water. Sugar in water. So, without thinking, you can say this number related to sucrose, which is solute, and water become a solvent. But mister, I remember you told me any information about of solute must be in mole, but now it's in gram. So what we have to do with this number? Well, dear student, it's a kind of challenging question. You have to turn this one into mole and this one into kilogram. So there will be two conversions. Turning 17.1 gram into mole and turning 200 grams into kilogram. Well, but in order to get number of moles, we need other information. You know what? Molar mass. So molar mass is 342.35 grams for sucrose. Well, firstly, so we have to calculate number of mole. Calculate mole mass over molar mass equals to, mass is 70.1 gram over molar mass is 342.35. Look, it's very easy. So first thing, we have to get number of mole equals to 0.05 mole. This is number of mole. And another thing, 200 kilograms must be converted into gram. So kilogram equals to gram divided by 1,000. And it will be, in this way it's better. It will be 200 divided by 1,000 equals to 0.2 kilograms. Well, mister, now I just followed your recommendation. I changed it grams to mole and grams of solvent into kilogram. So for what we did that? For what, please? For what we did that, mister? Well, we have to get molality. Molality. So the third step is molality. Molality equals to mole of solute per kilogram of solvent, which is 0.05 over 0.2 equals to 0.25 mole per kilogram, or mole, a little m in italic mode. So now still we didn't do nothing except of preparing molality. So molality equals to 0.25. Okay? Look at these steps. Look at these steps carefully, so deeply, because I want to delete due to the lack of space, if it's necessary, of course. Well, and now we are looking for delta TF. Delta TF equal to freezing point of what? Of solution minus freezing point of solvent. So equals to another equation we have. Delta TF equals to Kf times molality. We are looking for delta TF. So which one is useful to get the value of delta TF? Surely we have Kf. Kf is negative 1.86 because of solvent is water, times molality is 0.25. So we can get value of delta TF here. It's very easy. So we can calculate delta TF equals to negative 465. I think 465, yeah. Negative 465 Celsius degree. This is value of delta TF. But another thing, let's calculate, it means delta TF is negative 0.465 Celsius degree. What means by this number? It means from 0, freezing point will decrease by this number. Delta TF equals to 0, negative 0.465. So from 0, if it freezes and the freezing point decrease by this number, what is your expectation? Look, I think you know something. This number below 0, what's the result? Well, let's calculate. Delta TF equals to freezing point of solution minus freezing point of solvent. Delta TF is negative 0.465 equals to freezing point of solution. We are looking for freezing point of solution. Well, I just put X minus freezing point of solvent. Oh, it's another problem we don't have. But look, solvent is water, so it's 0. Now X equals to negative 0.465 Celsius degrees. So water freezes by this number. Okay, if we dissolve 17.1 grams of sucrose, now you can see how freezing point decrease, lowers if we add something into a pure solvent. Another question. Another thing. Come on again. Okay. Look, another one. If 0.5 moles of non-electrolyte solute is dissolved in 500 grams of ether. Mister, now we don't have water as a solvent. Ether is a solvent. Okay, solvent is ether. But don't worry, it's super easy. I told you, if solvent is not water, so freezing point of solvent and Kf must be given by a question. Kf always is for solvent. Kf is for solvent always. So because of Kf it's for ether, so we can say ether is a solvent. And now another thing, dissolving this into this. Solute in solvent. We have solute in number of moles, mister. It's okay, yeah. But solvent, firstly, we have to convert into kilogram. I just make here, it's very easy. So kilogram equals to 500 divided by 1000 equals to 0.5 kilogram. It's very easy. And we have mole. So immediately we can get molality. Molality equals to mole per kilogram, which is 0.5 divided by 0.5 equals to 1 mole. Mister, it's very easy actually. It's easier than the other question. But look, still I haven't finished to read the question, but I calculate all of the following things because of they are mandatory everywhere. They are common steps in any type of questions. So don't worry. In anywhere, if you saw gram, immediately convert into kilogram, and solute must be in mole. That's all. Very easy. What is the freezing point of solution? We are looking for the freezing point of solution. So write both equations. Delta TF equals to KF times molality. First one. Second one. Delta TF equals to freezing point of solution minus freezing point of solvent. It's very easy. Solvent is 0. No. It's ether. It's not water. It must be given. Look. Freezing point of ether, it's negative 116.6. So it's solvent. Freezing point of solvent. Because of solvent, it's not water. That's why it's given. Otherwise, there will be lack of this information. This phrase will be absent if the solvent is water. But because of its ether, so it must be given. Even for KF, it's the same, please. So we are looking for, look. Before you're looking, I'm looking for different color. We are looking for freezing point of solution. So we need freezing point of solvent. Yeah, we have here. But delta TF, no. So we can get delta TF here and substituting here. This is not minus, please. It's not minus. So don't say, Mr. Ｈۆگر, written minus before front of both equations. I just separated them. That's why. It's just for a point. Okay. So we have to get delta TF here. Substituting here, then we can run this equation to get the value of freezing point of a solution. So we'll start by this one. Okay, let's start. Delta TF equals to KF is negative 1.79 times molality is 1. So delta TF equals to negative 1.79 same. I will delete this. Negative 1.79. It's delta TF Celsius. And now, if we substitute, if we introduce the value of delta TF here, we can get the middle member value, the middle member's value. So, let's substitute here. Negative 1.79. Again, I have to delete. I don't know why. I'll start by 7 always. Maybe it's my lucky number. Lucky number, okay. Negative 1.79 equals to freezing point of solution minus this number. Negative 116.6. So it multiply into inside of the bracket. So freezing point of solution equals to, just use your wonderful calculator, you can get this number, negative 118.0.9 Celsius. Actually, I just memorized this number, and because of I solved this question for many times, that's why I knew the results very easily and quickly. So that was the different question if we use different solvent. It's very easy. I think there's nothing. The last question about freezing point. Last and shortest. Let's see. A water solution containing unknown quantity of non-electrolyte. After that, I will tell you why always the solute is non-electrolyte. I told you there are two parts. We'll start by non-electrolyte, then by electrolyte. Because of the equations is not complete still, but these are just for non-electrolytes. A water solution containing an unknown, we don't know the quantity of solute, so it must be calculated. Unknown quantity of non-electrolyzed solute is found to have freezing point of, so freezing point of solution, look. A solution is found to have freezing point, so it's freezing point of solution. So freezing point of solution equals to negative 0.23. What is molar concentration of the solution? So molality. Well, so molality we know. In which equation we have molality? Well, firstly we have to get value of delta TF. Delta TF equals to freezing point of solution minus freezing point of solvent. Okay, equals to, okay, solvent is water, so it freezes at 0. Freezing point of, it's minus 0 without thinking. Freezing point of solution equals to negative 0.23. So delta TF will be the same number. If solvent is water, so freezing point of solution will be equal to the delta TF always. Because of any number, if we subtract 0 from any number, the number will be the same. So delta TF equal to negative 0.23 Celsius degree. And now let's substitute into the second equation. Delta TF equals to Kf times molality. We are looking for molality. What is the value of molality? So molality equals to delta TF times Kf will be, delta TF equals to negative 0.23. Kf is negative 1.86. Why? Why 1.86? In which part of this question we get this number? No, in nowhere. But because of solvent is water, look, a water solution. So immediately because of water, freezing point of solvent equals to 0 and Kf equals to negative 1.86. Because of solvent is water. Super easy. Without thinking, it's nothing. So molality equals to 0.12 mole per kilogram. That was the last question about freezing point. Hopefully you understand it very well. Actually, it's super easy. So maybe for you, for the first time, it will be a little difficult, but you know, just replay this video for second time, everything will be super easy. And don't worry, by next lectures I'm going to mention more questions, and I'll give you more ideas because of there are many things in common with boiling point. That's why it will be a revision for you when I talk about the boiling point. Look, for the boiling point we have same equations, except of changing freezing to boiling and some simple numbers. So next lectures will be for you will be just a quick revision, nothing at all. So please just watch my video carefully. I mean about the freezing point, and everything will be super simple inshallah. تاوانی داوتو بخواتان دەسپێرم هەر شاد و سەرفراز من خواتان لەگەڵ.
لێرە چ هەیە؟